300 million years ago, Earth didn't look unfamiliar. It looked impossible. The sky shimmered with wings wider than eagles, the ground trembled under centipedes the length of cars, and the air, thick with 35% oxygen, was so rich it could make modern lungs lightheaded and flames burn like fury. Insects weren't background noise. They were apex giants, outmuscling vertebrates, soaring, hunting, and thriving in a world that should never have allowed them to. But it did. For millions of years, nature ran a bold experiment. What happens when the atmosphere supercharges life? The result was a planet ruled not by teeth and claws, but by chitin and wings. Then, just as suddenly, it ended. No meteor, no mass extinction, just a quiet collapse triggered by the very thing that built it, the air. This is the forgotten era when insects ruled Earth, and how a small shift in oxygen rewrote evolution itself. They say monsters once ruled the Earth, but not the kind forged in myth or sculpted with fangs. These monsters wore armor, breathed through tubes, and filled the skies with the thunder of wings. The Carboniferous period, roughly 359 to 299 million years ago, was unlike anything before or since. Earth's continents were stitching together into a single titanic landmass, Pangaea, wrapped by a warm global ocean called Panthalassa. But the real transformation wasn't in the tectonics, it was in the air. Thick, wet, and teeming with oxygen, the atmosphere reached concentrations as high as 35%, far above today's 21%. That simple difference didn't just change how fast things burned or how deeply creatures breathed. It flipped the laws of life itself. Forests exploded with growth, forming vast, swampy jungles of towering club mosses, tree-sized ferns, and primitive horsetails. These weren't trees as we know them. No flowers, no seeds, just hollow stalks growing 30 meters high and blanketing the equator in a soggy green gloom. The air was humid, the ground spongy with peat and decay, and under the dense canopy, life evolved in shadows. Giant fungi, some taller than a man, sprouted in the wet soil, while amphibians newly arrived on land slinked through underbrush like lost prototypes of reptiles. But the true rulers of this world weren't vertebrates. They didn't need bones. They had exoskeletons. Insects, arachnids, and millipedes surged into ecological dominance, their size supercharged by the oxygen-rich atmosphere. Enormous dragonflies, like Meganeura, soared overhead with wingspans stretching up to 70 centimeters, nearly the length of a human arm. On the ground, multi-legged tanks like Arthropleura crawled through the undergrowth, growing up to 2.6 meters long, the largest land invertebrate to ever exist. Some moved slowly, eating decaying plants. Others hunted, giant scorpions armed with serrated pincers and venomous tails stalked prey among the ferns, while the skies buzzed with soft-winged predators whose eyes could spot movement from any direction. And still, life had barely begun to explore the possibilities. Deep in shallow pools and slow rivers, sea scorpion relatives like Megarachni swept through the sediment. Not quite spider, not quite anything we'd recognize, yet large enough to unsettle any sense of scale. All of it, every crawling, gliding, skittering creature, thrived because the atmosphere allowed it. And that's the part we rarely think about. Oxygen isn't just background, it's architecture. Modern insects breathe through passive diffusion using narrow tracheal tubes to pull in air directly to their cells. That system doesn't scale well. In today's oxygen levels, their size is biologically capped. But in the Carboniferous, that limit shifted. With 35% oxygen, their inefficient systems suddenly worked in their favor. Larger bodies could finally be supported. Insects grew, literally, into a new class of life. Some scientists call it a biological oxygen window, and in that window, arthropods ruled. Their muscle structure allowed for pound-for-pound strength, unmatched even by modern apex predators. Dung beetles today can pull over 1,000 times their body weight. Imagine what their prehistoric ancestors were doing with double the oxygen. But all of it was precarious. The very ecosystem that created this oxygen boom was fragile. Forests soaked in moisture, forming deep peat beds that trapped carbon and released oxygen in return. As more plant matter was buried and compressed, coal formed beneath the swamps. And yet, even this abundance carried seeds of collapse. As Pangaea continued to form, mountains rose and weather patterns shifted. Rainfall dropped, and what was once a unified tropical forest began to fracture. Wetlands dried out. The thick, living, breathing forests thinned. And slowly, oxygen began to fall. Not all at once, not in a cataclysm, but enough that the oxygen window that had enabled these insect giants to thrive began to close. Slowly, the atmosphere returned to something less flammable, less heavy, less generous. And as it did, the balance of life tilted. But for tens of millions of years, before dinosaurs, before birds, before mammals whispered into existence, this was their time. A world of damp green skies and predators with wings. A planet shaped not by what lived in it, but by what filled its lungs. We tend to think evolution favors the fittest, but fitness depends entirely on the environment. And during the Carboniferous, oxygen rewrote the rules. The insects that swarmed this ancient world didn't grow huge just because they could. They did because for the first time in history, the atmosphere allowed it. Modern insects, from houseflies to beetles, don't breathe the way mammals do. They lack lungs. Instead, they use a delicate network of hollow tubes, tracheae, that branch through their bodies like plumbing, carrying oxygen straight to their tissues by simple diffusion. It's a beautifully simple system, but it breaks down as size increases. The bigger the insect, the harder it is for oxygen to reach the center of the body without pressure or active pumping. That's the limiting factor, scale. In today's atmosphere, with only 21% oxygen, insects hit a hard biological ceiling. But when Carboniferous air reached 35%, it changed everything. That increase didn't just help insects survive, it acted like a biological steroid, enhancing their efficiency, their reach, their size. Fossil records confirm the result: winged giants, arm-length predators, ground crawlers as long as sofas. For decades, this idea was theoretical, an elegant explanation for ancient gigantism. Then in 2007, a team of researchers at Arizona State University decided to test it. They raised insects, beetles, dragonflies, and more in controlled lab environments with elevated oxygen levels, simulating prehistoric atmospheres. The results were stunning. Insects raised in hyperoxic conditions grew significantly larger, faster, and in some cases even changed behaviorally, eating more, moving more, dominating their tanks. It was proof. Oxygen isn't just life support, it's a growth switch. With enough of it, passive breathing becomes powerful. Arthropods could expand into sizes previously thought impossible, and some species did so rapidly. But this window had limits. Even as insects grew, vertebrates were catching up. Amphibians were evolving into reptiles, creatures with better lungs, watertight skin, and internal circulation systems that could support larger, more complex bodies without needing atmospheric crutches. Unlike insects, vertebrates could scale up independently of the air around them. And once they did, the race was on. But in the Carboniferous, insects still had the edge. Their exoskeletons gave them unparalleled strength-to-weight ratios. Their compound eyes offered nearly panoramic vision. Their flight mechanics, especially in species like Meganeura, rivaled even modern birds and drones. Each wing beat wasn't just instinct, it was engineering. These insects weren't primitive, they were pioneers. Evolution was testing flight, armor, and predation all at once, and for a while, arthropods were winning. Still, the tracheal system had a ceiling. The very mechanism that gave them strength also made them vulnerable to change. A drop in atmospheric oxygen wasn't just inconvenient, it was lethal. Unlike vertebrates, insects couldn't compensate with deeper breaths or more efficient hearts. The air around them was their bloodline. And as Carboniferous forests began to shrink, fragmenting due to shifting climates, rising mountains, and drying weather, the planet's oxygen engine began to sputter. Less vegetation meant less carbon burial. Less burial meant less oxygen release. And as oxygen levels dropped, the tracheal system faltered. The giants began to vanish. Species that had once ruled the skies and shadowed the forest floor began to shrink or disappear entirely. It was slow, not an extinction, but a dethroning. By the early Permian, the oxygen high had ended. Insects didn't go extinct. They adapted, scaled down, grew smarter, faster, more diverse. But they would never again reach the towering sizes of their Carboniferous ancestors. Today, we still see echoes. Dragonflies with ancient wing designs, beetles with muscle structures nearly unchanged, scorpions that still use the same ambush tactics as their 70-centimeter cousins. But the air they breathe no longer lets them grow into monsters. That era is sealed in coal seams and stone. Still, the blueprint lingers in their DNA, and it tells us something profound. Atmosphere isn't background, it's destiny. Oxygen didn't just fuel life. For a brief, wild moment, it defined it. Step into the Carboniferous forest, and the scale of life warps instantly. This wasn't a world designed for humans. It was a kingdom of giants, all built on chitin and instinct. Look up, and you might spot Meganeura, the undisputed monarch of the sky. With a wingspan nearing 70 centimeters, this ancient dragonfly-like predator flew not with fluttering awkwardness, but with calculated precision, 4 wings moving independently, giving it the ability to hover, dive, and strafe with deadly accuracy. Fossil evidence suggests Meganeura was a ruthless aerial hunter, feeding on other insects, early amphibians, and perhaps even vertebrate hatchlings. Its compound eyes were enormous, almost spherical, giving it a panoramic battlefield view. In modern terms, it would have been the fighter jet of the Carboniferous canopy. But the danger wasn't only in the skies. On the forest floor, beneath rotting ferns and fallen club mosses, moved a creature so massive it was once mistaken for a log. Arthropleura, the largest land invertebrate to ever exist, stretched up to 2.6 meters in length. Like a centipede cast in armor, it crawled slowly, crushing vegetation beneath its dozens of legs. Despite its terrifying appearance, it was likely a detritivore, feeding on decaying plant matter, moss, or fungi. Still, its size alone made it nearly untouchable. No known predator would dare challenge it outright. And lurking in the underbrush, Pulmonoscorpius, a scorpion the size of a house cat, waited. Covered in thick interlocking armor plates and armed with muscle-bound pincers and a venomous stinger, it was an apex ambush predator. Fossils suggest it crushed prey with serrated claws and injected venom to finish the kill, using motion-sensitive hairs to detect even the slightest vibration in the soil. This was not the kind of scorpion you step over barefoot. These weren't primitive creatures, they were refined products of their atmosphere, every limb, wing, and jaw designed by millions of years of oxygen-fueled evolution. And yet, for all their might, they existed within a fragile balance. They didn't roar or stomp like dinosaurs, would millions of years later. They hissed, they clicked, they struck from shadows, they ruled not through brute force but through adaptation, a reign made possible not by strength alone, but by the air itself. Today, their fossils lie compressed in coal beds, their size reduced to numbers in textbooks, their threat softened by time. But in the Carboniferous, they were more than curiosities. They were the peak of their kind. Evolution doesn't play favorites. It simply plays with whatever tools are available. And in that one chapter, when oxygen turned up the dial and the forests grew wild and deep, these creatures weren't mistakes or monsters. They were inevitable. And yet, even as the canopy thickened and the shadows deepened beneath towering club mosses, the delicate equation that gave rise to these invertebrate giants was already shifting beneath their many feet. For while evolution had handed arthropods a fleeting empire, it had not paused its relentless experimentation elsewhere. Among the damp leaf litter and the still ponds of the late Carboniferous, a quieter revolution was unfolding, not in size, but in structure. Tiny, scaly creatures with internal lungs, shelled eggs, and drier skin were beginning to crawl into the margins. These early reptiles, barely the length of a forearm, lacked the monstrous presence of Meganeura or Arthropleura, but they carried a secret weapon: independence from water. Unlike the amphibians that had dominated the undergrowth until now, creatures still tied to moist environments for reproduction, these newcomers laid amniotic eggs, carried their own miniature ecosystems inside them, and could thrive in dry, open spaces. Where insects and amphibians had ruled the swamps, reptiles would soon claim the hills. But the transition was subtle at first, masked by the sheer biomass of the arthropod world. Still, the atmosphere continued its gentle decline. Global cooling events, likely driven by tectonic uplift and altered ocean circulation, disrupted rainfall patterns and slowly drained the lush, equatorial wetlands. Peat beds stopped accumulating, coal formation slowed, and the oxygen feedback loop began to collapse. Fires, once frequent and ferocious, dwindled as the air thinned, and with less oxygen, the insects began to shrink, not because they chose to, but because they had no other choice. Their bodies, so perfectly tuned to a high oxygen world, simply couldn't scale down their biology fast enough. The enormous tracheal systems that once made them kings now left them gasping, sluggish, and vulnerable. Their golden age was ending. By the Permian period, the forests had receded, the swamps had withered into scattered basins, and vertebrates, leaner, meaner, and internally pressurized, rose to fill the void. Reptiles diversified rapidly, giving rise to sail-backed predators like Dimetrodon and the first archosaurs, the lineage that would eventually birth crocodiles, pterosaurs, and dinosaurs. But even as their dominance faded, insects did not disappear. Instead, they pivoted. Evolution reshaped them into smaller, faster, more efficient forms. Wings evolved into foldable structures for protection. Mandibles became specialized for slicing, sucking, boring, and stinging. Social structures began to emerge, first in wasps and ants, then later in termites and bees, laying the foundation for some of the most complex, non-human societies on Earth. Even in retreat, insects refused irrelevance. Their adaptability proved greater than their size, and as Earth's climates shifted again and again over the next 250 million years through extinctions, ice ages, and asteroid impacts, they persisted. They became pollinators, recyclers, parasites, and predators. They infested the nostrils of dinosaurs and the feathers of early birds. They fed the first mammals and would later torment them. And they did so with blueprints drafted in the Carboniferous: compound eyes, segmented armor, tracheal breathing, and that ancient unmatched strength-to-weight ratio. Today the titans are gone, but the genes remain. You can see their legacy in the way a dragonfly hovers above a still pond, its wing beats echoing a 300-million-year-old rhythm. In the spiraled mandibles of a beetle cracking open a seed pod, in the perfect geometric lattice of a wasp's nest, in the hiss of a cockroach scuttling through a sewer, descended not from weakness but from resilience. And even now, the atmosphere continues to shape them. Urban insects have already begun evolving pesticide resistance, changes in body size, even altered circadian rhythms to match artificial light. Some scientists argue that cockroaches in New York and London are diverging into city-specific subpopulations. Evolution never sleeps, and so the story loops back on itself. As we pump CO2 into the skies and alter the chemistry of Earth's breath once again, the descendants of the Carboniferous swarm in gutters, gardens, and glowing screens. What will happen if we shift the atmosphere once more? Could another oxygen window open? Could gigantism return? Likely not. The planet we've built is not the one that birthed Meganeura. But the lesson lingers like coal smoke in an old fire. The rules of life are written in air. When oxygen rose, the insects grew, flew, and ruled. When it fell, they faded. Not by failure, but by design. They adapted because they had to, and that adaptability is why they still outnumber us, outsurvive us, and, in biomass and biodiversity, still rule in ways we can barely comprehend. The age of giants may be over, but the empire of insects never ended. It merely changed form. And if Earth breathes a new rhythm in the ages to come, they will be there, listening with filamented antennae, waiting to rise again. Not as relics, but as reminders that nature's boldest experiments never really die. They simply molt, shrink, and bide their time.